Hello, and welcome to this video about the squeeze theorem. When calculating limits, occasionally we run into examples that cannot be evaluated by the more conventional methods. Direct substitution is inconclusive, algebra proves fruitless, even graphing may not give a clear picture. Sometimes we can actually squeeze a function between two other functions to determine a limit. For this reason, the theorem is also referred to as the sandwich theorem, the sandwich rule, the police theorem, the pinching theorem, the squeeze lemma, and in Italy, the theorem of carabinieri. Let's see it in action with a familiar limit we know before stating it formally. We know that the limit as x approaches 0 of sine of x over x equals 1. Substituting 0 yields the indeterminate form 0 over 0. But we can't use algebra to find the limit because the numerator and denominator can't be simplified. We can see the limit on a graph. We can use L'Hopital's rule. The limit as x approaches 0 of sine x over x equals the limit as x approaches 0 of the derivative of sine x over the derivative of x, which equals the limit as x approaches 0 of cosine x over 1, which equals cosine of 0, which equals 1. Another option is to use the squeeze theorem. This graph shows that sine of x over x is between the cosine function and the horizontal line y equals 1. When looking for the betweenness, we'll zoom in close to x equals 0. No matter how close we zoom into the graph, sine x over x will always be between cosine x and 1. By between, we are referring to the function outputs. Let's zoom in numerically. Of course, we can't use 0, but we can use numbers really close to 0. No matter how close to 0 we get, the values of g of x are always between the values of f of x and h of x. So what does this do for us? Well, since we know these two things, we automatically know that the limit as x approaches 0 of sine x over x equals 1. Sine x over x is between cosine x and 1 around x equals 0. The limit as x approaches 0 of cosine x equals the limit as x approaches 0 of 1, which equals 1. Sine x over x is squeezed between cosine x and 1 around x equals 0. Since cosine x and 1 both approach 1 as x approaches 0, then sine x over x must as well. It's sort of an indirect way of finding a limit, and it's easy to see why names like squeeze, pinch, sandwich, and police are used to describe the theorem. Now for the formal statement. If f of x is less than or equal to g of x is less than or equal to h of x, and the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals L, then the limit as x approaches a of g of x equals L. Using the theorem often involves more of a proof-like approach than a method, and there are often many ways to use it to prove the value of a limit. For example, with the previous limit, we didn't need to use the functions cosine x and 1 as upper and lower bounds. We could have used x squared plus 1 and negative x squared plus 1 since they both approach 1 as x approaches 0, and sine x over x is between them. Let's use the squeeze theorem to find the limit as x approaches 0 of x squared times the cosine of 1 over x. The table and graph show the function oscillates around the x-axis, but the limit is 0. Using substitution in algebra is fruitless, so we'll begin with the cosine of 1 over x piece, because that x in the denominator is what's really complicating things. Based on our knowledge of the cosine function, we know that cosine of 1 over x is between negative 1 and positive 1. Now we're going to multiply all three parts of this sentence by x squared, because the result will be the original function. So negative 1 times x squared is negative x squared. This gives us x squared cosine 1 over x, which is our original function. And 1 times x squared is x squared. This tells us how to squeeze the function. Put it between negative x squared and positive x squared. Let's take a look. According to the theorem, we know this. We know that the limit as x approaches 0 of negative x squared equals 0. That's because we plug in 0 for x, and that gives us 0. We also know that this is equal to the limit as x approaches 0 of positive x squared, because again, you plug in 0 for x, and you get 0. So now, because of the squeeze theorem, we know that the limit as x approaches 0 of x squared cosine of 1 over x is also equal to 0. And that's because it's between these two functions that go to 0, and so therefore this function also has a limit of 0. Suppose f of t is equal to negative 2/3 t cubed plus t squared plus 1/3, and h of t is equal to the cosine of t pi over 2. If f of t is less than or equal to g of t is less than or equal to h of t, use the squeeze theorem to show that the limit as t approaches 2 of g of t is equal to negative 1. Now we don't know what g of t is, but with the squeeze theorem we can prove this limit. All we need to show is that the limits of f of t and h of t are the same as x approaches 2. Since we know that g of t is pinched in between them, if those limits match, we'll have our limit. Let's start by looking at the limit as t approaches 2 of f of t. So if we do that, we have the limit as t approaches 2 of f of t. So we're going to plug in a 2 anywhere we see a t for this function. So negative 2/3 times 2 cubed plus 2 squared plus 1/3. This gives us negative 16/3 plus 4 plus 1/3, which simplifies to negative 1. Then we're going to look at h of t. So the limit as t approaches 2 of h of t. Again, we're going to plug in a 2 anywhere we see a t. So the cosine of 2 pi over 2 simplifies to the cosine of pi, which again is negative 1. Since the limits of f of t and h of t are both negative 1, and they are squeezing g of t, then we can note that the limit as t approaches 2 of g of t also equals negative 1. Let's try one more. If negative x squared over 4 minus x over 2 is less than or equal to f of x is less than or equal to the square root of negative 1 over 9x, use the squeeze theorem to find the limit as x approaches negative 1 of f of x. We're going to start solving this problem by finding the limit as x approaches negative 1 of this function. So the limit as x approaches negative 1 of negative x squared over 4 minus x over 2. Plug in negative 1 anywhere we see an x. So then that gives us negative 1 over 4 minus negative 1/2 turns into plus 1/2, which equals positive 1/4. Then we're going to find the limit as x approaches negative 1 of this function over here, of the square root of negative 1 over 9x. Again, plug in a negative 1 for x, and we'll get the square root of 1 over 9, which is equal to 1/3. In this case, f of x is between the two functions, but it's not being squeezed. Since their limits as x approaches negative 1 do not match, the best we can say is that the limit as x approaches negative 1 of f of x is between 1/4 and 1/3. Thanks for squeezing a little time out of your busy schedule to explore this theorem. I hope that this video helped you understand when it's needed and how it works. See you next time.